what is a histogram? So histogram is nothing but the frequency distribution of your house prices. So what you do is, you have got different house prices, right? So let's say I'm just kind of writing down different things: 160, 170, 180, 140, 145, 146, 181, 192, so on and so forth, right? So what you do now to construct histogram is basically you see the minimum price is 140 and you see maximum price is 192. So you say maximum price, let's say take 200, and you'd split this up into 10 different bins, right? So 150, 160, 170. So each of these are called bins, right? So you are basically splitting in bins of 10, right? So every bin basically constitutes of 10 values: 170, 180, 190, right? So now you have got what? 1, 2, 3, 4, 5, 6 bins. Now in 140 to 150, you see that there are 3 house prices, right? In fact, so you have got this one particular house price, 140, then you have got 140, 145, and that's it. So you have got 3 houses. So you basically build a frequency table which is corresponding to 3. Now between 150 to 160, you have got 1 house price, and this is 2, right? So you have got 2. Now between 160 to 170, you have got just 1. So you just got 160 here. So 170 to 180, again just 1. And 180 to 190, again 1. And 190 to 200, again 1, right? So that's the thing. So you have 2 and you have got 1 out here, right? So this is called a frequency. So what you did was, for each of the bins, right? So you basically figure out what were the number of houses in this. So in this case, 140 to 150, there were 3 houses. So this was a frequency. So you basically plotted this bar which went up to 3. Then in this bar, you plotted it to 2. So this is called a histogram, right? So that's the understanding of histogram. And now we plot this thing using 60 bins, right? So we have basically divided the data into 60 different bins. In our example, the one we drew, there were 6 bins, right? So in this case, we divide the data into 60 bins of histogram and we plot this. So what we can tell from this 60 histogram is that something, so altogether we have somewhere around, so we have already talked about all of these frequencies, right? So what do each of those height of those histograms represent? So the height of each histogram is the number of houses that basically have the sales price between 140 to 150, right? In this particular example, that's something that you were very clear with, right? So altogether, so we know that from the range of price 34,000. So if you look at this particular bin, 34,900 to, you can probably see it from the graph, but probably there's a bin which is starting from 34,900 to 106,000. Sorry, 34,900 to 106,000. We have 148 observations, right? So now, by just looking at the histogram, we can tell if the histogram is not picked around the center of the range or not, right? So peak is basically, in this particular case, is the left of the plot, right? You can see our histogram. This was also basically the case where the peak was basically towards the left of the histogram, right? And there were a lot of values. So in our example also, if you look at this diagram clearly, you can see that it's peak to the left, right? So what does that kind of say? The peak to the left is basically indicating that it's a positively skewed histogram. Now what is positively skewed and what is this mean, median, mode and all of that? We are going to talk about that in a while. So analyzing the histogram, we see that our histogram is positively skewed, right? So because it was peak to the left, we can see different examples of skewness from the image and see how mean, median, mode are affected. Mean and median, at least we understand about what is mean and median. So let's see what happens with mean and median. So obviously you can see that if there's no skew, it's the normal distribution. In this case, you have basically mean and median basically on the same line. But in case you have a positively skewed deviation, your mean kind of is shifted to the right, because there are a lot of basically outlier values to the right. That's why it's skewed like this, right? So there's a long tail out here that you can see. The long tail basically means that there are a lot of house prices there are house prices with very less frequency, but there are a lot of them which are highly priced. So there are a lot of expensive houses, probably not very high on frequency. That's why the frequency is very low, but there are a lot of them, right? So that's why this tail kind of goes up and up, right? Because on the x-axis is basically the price of houses, on the y-axis is basically the frequency of houses, right? You remember this curve. So this is basically the price of houses and this is the frequency. So basically the frequency is low, basically means that there are expensive houses but not very frequent, right? So that's why we see a positively skewed houses, and that's why we see our mean is roughly 180,000 whereas median is 160,000. So John was really not bothered about checking the mode of his data, but let's cover that concept quickly. So what is mode? Mode is basically nothing but the most frequently occurring data point in a given data set. So let's again go through the concepts. Okay, we'll go through that in a while, but let's first understand mode. We arrange the data in the increasing order, and then we just pick out the data which occurs a maximum number of times, right? That's the concept of mode. Any value that occurs maximum number of times is your mode, right? For example, this is the data that you have see here, and in this grouping you can see that 15 is occurring 2 times, 11 is occurring 1 times, 27 is occurring 2 times, but 19 is occurring 4 times. So that means 19 is the mode, right? Because it's the most frequently occurring data, right? Most frequently occurring frequency, right? So basically in case of a histogram, if you are doing this, so basically any value, the highest frequency bar diagram, right? So if this is the highest, so this is the highest, right? So basically the middle value of this particular diagram is your mode, right? So mode is basically dependent on the frequency, and frequency is exactly what we kind of plot in histogram. So basically the bar, the bin which has the highest frequency, the middle value of that particular bin is your mode, right? In case of a histogram, in case of a values which are just like this, you can directly get to the mode, right? You don't need to do the histogram. So basically any value that is occurring maximum number of times is called a mode. Obviously in case there are more than one value which are probably high, so if in case instead of 19 occurring say 4 times, say 19 occurred only 2 times, right? So then for 15, 19 and 27 would have been modes, right? All 3 of them would have been modes, right? Because all of them occurred twice. So then in this case, if they were tied, then the most frequent, if there are 2 modes, it's called bimodal. If there are 3 modes, it's called a trimodal data, right? So in this case, we can directly get the mode, and the mode is 14,000. Sorry, 140,000. That's even lower, right? So our mean was 180,000. Mean basically was the average of all processes. That was 180,000. Median was the value that separated our 50% of the data, and that was around 160,000. Mode is basically the maximum number of houses that occur at any price, and that we see is the maximum houses are actually at 140,000, right? So that's the difference between the different 3 measures of central tendency. So all of these measures are basically measures of central tendency. Mean is basically average of all your prices. You take the prices, you add them up, divide by the total number. Median is the one that sits right in the middle of your data. It splits in data into 2 equal parts, right? 50% of your data on the left, 50 on your right. And mode is the one that has got the highest frequency, right? Whichever value that is. So in this case, 140,000 is the price where most of the houses are. So mean, median or mode, what to use when, right? So the best measure of central tendency is not a definite answer. Obviously nothing in data science is a real, like you never can answer with a single answer, right? Obviously had there been a single answer, you would not have been studying the rest of the cases. So because there is no single answer, that means that the best answer kind of depends on the type of data you are using. So let's dive deeper and intuitively figure out what is the best measure of central tendency. So the mean is usually the best measure of central tendency to use your data distribution is continuous and symmetrical. Understand this though here, that if your data is not continuous, you really cannot use mean, because in mean you have to add values, right? So now if for example, if you have your prices, for example, if you have values like your houses, colors of houses, right? And that's your distribution. So colors of houses could be red, blue, yellow and all of that. Now you cannot add red plus blue plus yellow, right? There's nothing in that. There's nothing, no meaning out of adding red plus blue and dividing by 3. Similarly, you cannot do median, because median basically first needs them to be ordered in an ascending order and then splitting, then basically looking at the 50%. Now you cannot order in the first place, right? So you do not know if red is better than blue or blue is better than green, right? So there's no way you can ascend. But you can definitely do mode, right? Mode is basically checking what is the maximum number of houses colored, right? Are they colored red, are they colored blue, or are they colored green, right? So that's why you can always calculate mode, but mean and median you can only calculate if your data is continuous. So that's the first thing. So if your data is continuous and symmetrical, then you can obviously mean is a good measure to use. However, it all depends on what you are trying to show from your data, and we would probably learn more about normal distributions in the session on inferential statistics that we do next up after this. So there, when you learn it, you would probably be better able to appreciate what is a normal distribution and what is a symmetric distribution per se. When is the mode? So that's if your distribution is basically normal and symmetric, the idea is you can use mean fairly reliably. What is mode? The best measure of central tendency. Mode is the least used measures of central tendency. The mode will be the best measure of central tendency when dealing with nominal data, right? Which is what I explained to you. Something that is cannot be ordered, right? Red, blue, green. If you cannot order the data, that means it is categorical data, and it's not even ordinal data. Ordinal data is something that is categorical but can be ordered, right? For example, education. Education, you can have primary, secondary, and all of those, and there's an order, right? But colors of houses are not even orderable. So in case you have a nominal data, you have only left with no other option but use mode, right? So mean and median are normally preferred when dealing with all other types of data, but this doesn't mean mean is never used with other data types, right? So what is nominal data? Nominal variables are variables that have two or more categories but which do not have an intrinsic order, right? So which I already explained to you right now, the colors of houses. For example, a real estate houses could classify their types of property into distinct categories such as houses, condos, co-ops, or bungalow. So type of property is a nominal variable with four categories called houses, condos, co-ops, and bungalows. Of note, the different categories of nominal variable can also be referred to as groups or levels of nominal variable. Understand this, the fundamental point is this is a categorical variable, which means that it can only take 5-6 different values. And those 5-6 different values cannot be ordered, right? So there's no order in them. As I said, color of houses, there are 3 possible values, red, blue, green. You really do not know which one to order. But for example, education can come in, again, it's a discrete variable, right? It can come in 5 different values, which is primary education, secondary education, graduate degree, postgraduate, and all of that. Now there's a certain ordering, right? You know, primary education is lower than secondary education, which is lower than graduate, and so on. So there's an intrinsic ordering. So those are called ordinal variables, where you can order your categorical variables. So categorical variables are divided into 2 types, ordinal and nominal. Ordinal are those categorical variables which you can order, nominals are the one which you cannot order. So when is median the best? Now that you've understood when to use mode, when to use mean, when to use median, the median is usually the one preferred to other means of central tendency when your data set is skewed. So if you are dealing with a continuous data, but that data set is skewed, there are a lot of outliers, then you cannot use mean reliably. That's the case where you want to use median, right? So we already know what skewed data is. However, a mode can also be appropriate in this situation, but is not a commonly used one as median, right? So just keep that in mind. Mode you can apply in any kind of distribution. If it's continuous, if it's nominal, ordinal, anything that is there, you can. Basically, you are just checking out for which value is maximally occurring, right? It could be continuous, discrete, doesn't matter. You cannot apply mean and median to nominal distributions. For nominal, you can only and only apply mode. For continuous distribution which are symmetric, you may go ahead with mean. If they are skewed, you can do more median. You can do mode in any which case. Doesn't matter, but mode is normally not the preferred one. Mode is basically when you are left with no other option. So I have already talked about this. So basically, median is the one that if you have a lot of outliers, depending on how influential your outliers are, you probably would want to, if there are a lot of outliers and they think that they probably might significantly distort the mean, you might want to use median in those cases. So in a normally distributed data set, which is greatest, mode, median, or mean? If the data set is perfectly normal, now you really do not know what is a normally distributed data set. We'll learn about this in the next lecture. So normally, just to kind of give you an idea, normal data sets are basically the data sets which are absolutely symmetric, right? So this is a data set and this is a histogram, right? So let's say histogram looks like this, something like this. So basically the maximum of your population lie in the middle, and then the population kind of goes down as you kind of go on both sides, right? So if your histogram looks like this, then then you can conclude that this is a perfectly normal distribution. In case of a perfectly normal distribution, your maximum population lies in the middle. So basically your mode is here because this is the highest population, and this, because it's a middle, your median is also here, and because it's symmetric on both sides, it's not skewed to the right or left, your mean is also here, right? So mean, mode, all of them coincide in case of a perfectly normal distribution. So basically your histogram is like, so normal distribution examples are number of scores in a normally given test, right? In any academic test in your school, college, always marks of students are always in a normal distribution. Maximum people have the marks in the middle, and there are people who perform very bad, and there are people who perform very good, and the frequency of those people are kind of very low. As you come towards the center where people are performing bad, like in the middle, the frequency of those kind of people extremely high, right? So as to say, mediocre people are the most high. There are people who are extremely bad, and people who are extremely good are kind of low, right? So for any data, that's in those kind of data sets, it doesn't matter which is greatest, mean, median or mode, they're all equal. For any data set which measures of central tendency have only one value, median and mean can only have one value, but not mode. Mode is basically the value that occurs maximum number of times. Now in case there are three values which occur equally high, then all three are modes, right? So then it's a trimodal distribution. So now let's plot the mean, median and mode in case of John's data. So you remember John's data was positively skewed, right? So that means it had a long right tail. So in case it has a long right tail, you probably see that what we are expecting to see here is that mode is towards the left extreme, and then we have median, and then we have mean, right? So those are the three lines that we have plotted here, and you can see here. So now John thinks that he has found his dream house, right? And he cross checks the price and gets to know that it's for 250,000. Now that's stupid, right? Because he just checked that the average price, right? The average price was 180,000. The median was 160,000. The mode was 140,000. But his house is for 250,000, right? So that's a very different price from his expected prices, right? So now he wants to check how far the price of this house is from the mean when compared to other points in the data set, right? So again, take a minute to read that, and I probably go over it once again for you. He wants to check how far the price of this house is. So this particular house, which is 250,000, compared to how far other prices are. So probably you could have, there are two possible kinds of distributions, right? One, where you have your value as mean, right? So this is your mean, and you have got maximum people, and then most of the other houses are basically something like this, right? So you have your distribution which looks like this. So this is a distribution. So almost all your houses are in the mean, right? And then the other houses could be this, where you could basically have something like this, right? So basically you have very small number of houses at the mean, and there are equally large number of houses, almost similar frequency houses on the both sides, right? In here, probably every houses are basically between, say, this is 180,000, right? So between 160 to 200, and here all the prices are basically from 100 to 260. That's it. So 260, 100,000 to 260,000, right? So there are two possible variations, right? You can understand this. So in this case, the spread is very low, right? Because all your houses are well within this particular boundary, right? So there's 180,000 is a mean, and there. So mean in both the cases are same, right? But in this cases, the house prices are very strongly centered around mean. So all your house prices are absolutely near the house price. So all house prices look like, all houses are exactly similar to each other almost, right? There's very little variation. In this case, the variation is very high, even though the mean of those two cities are basically exactly same, right? So this is 180,000. So in these two cities, the average is exactly same. But in this case, the variation is very small. In this case, the variation is extremely high. So how do we measure this, right? So that's exactly what John is kind of figuring out. So spread of the data. So mathematically speaking, he is basically trying to do this. So his house price is 250,000 minus mean by random variation, right? So he is basically trying to check how far is his house as compared to variation in the data set, right? So his house price is somewhere around here, right? 250,000 is here, right? So basically in this case his house price is extremely deviant from, if this is the scenario, then his house price is very high as compared to the random variation in the data set. In this case, if his house price is here, well, it's not as random, like there's a definitely lot of houses above that price also, right? So as compared to the random variation in the data set, his house is not very expensive. But in this case, his house is extremely expensive, right, as compared to the rest of the houses. So this is what he's trying to measure. He's basically trying to see as what is this variation that is here, and as compared to the variation, how expensive is his house, right? So we know what's a mean here. We have found that before. But what is this random variation, right? So random variation is nothing but the average of the variation of the data from the mean, right? So how do we measure this? That's the next question. So first off is range is the easiest way of and most naive way to kind of check the spread of a data, right? So the most easiest and most probably one of the naive ways is basically check the range. Range is basically the minimum value minus maximum value. So 200 minus 160, which is in this case 40,000. And in this case the maximum value is 260 and 100. So in this case 160,000, right? So this is range. So from range we can basically get an idea of how varied the data set is, right? In this case the range is high, which means that there are a lot of prices in the data set. In this case the range is very slow, which means that there are very small, the house prices are almost similar to each other. So in this case, let's check the range, which is np.max gets you the maximum value, np.mean gets you the minimum value, and you get the range, and that is 720,100. So that's one way of calculating range. Fair enough. Is there any other way of calculating this variance? Well, there seems one easy and intuitive way, right? Just take the difference of each of the values from the mean and see how that comes out. But honestly, this couldn't be any more wrong. And understand this why. I would let you do that calculation at your end right now before we proceed further. In fact, I would suggest you do this before you kind of see the final solution. So if you break down the formula, you basically see that, let's understand this. 1 by n into what we are trying to do here is 1 by n into summation of xi minus x bar, right? So summation of xi minus x bar, so 1 by n into summation of xi minus x bar. So if x bar is a constant, right? So what you do here is, if you do this, you would basically come out to be x bar into n, right? So if this is a constant which you are summing up multiple times. So this is basically nothing but, understand this, x1 minus x bar plus x2 minus x bar, right? That's what you're trying to do. Now you see this, what you're trying to do is this by n, right? So x bar is counted three times, right? So you would basically have n number of times x bar by n, right? So this would cancel out. Now summation of xi by n is nothing but x bar. So x bar minus x bar comes out to be exactly 0, right? So this is a definition of average. Average is basically nothing but x1 plus x2 plus x3 by n. And that is awesome. So this is x bar but minus x bar, so that is equals to 0. So this is not a good way to measure values, as values are always centered around the mean. So we need to get rid of the sign. So one way is basically, instead of doing this particular thing, we can directly take the absolute values, right? We can take absolute values. Now that is also not a very good idea. Here n equals to 3, right? Just keep that in mind. So this was the case. So we can add directly the absolute values, but then absolute values have a problem, and we'll kind of realize that much later. Mathematical difficulties. So what do? We instead of adding directly the absolute values, we take a square of these values and add that, right? So this is called the variance, right? It's the mean squared distance of the observations from the mean. So what we do is basically take every observation, take its distance from the mean, the difference from the mean, and square it. and add it. And this is the formula for variance, which is already what you have seen here, right? Which is 1 by n summation of xi minus x bar square, right? You are familiar with this notation now, summation from I equals to 1 to n, right? So which is basically nothing but x1 minus x bar square plus x2. This same equation that we have drawn out here, right? It's the same thing by n. So that's the concept of variance. So now you calculate this. In John's case, the variance is calculated in terms of dollar squares, right? So this isn't practical because obviously what you're calculating here when you're doing this, right? Summation of xi minus x bar square by n. This is your variance, right? Sigma square. That's what you call it. Now the problem is this difference is in billion, and then say whatever 1,000 million, whatever price range it is in, and then you get square it, right? So that is something that is wrong, right? So that's not practically usable. So what you want to do is, instead of using the squares, you want to take a square of this thing, summation of xi minus x bar square by n, and this is called sigma, which is nothing but standard deviation. Standard deviation is nothing but the square root of the summation of differences from the mean, right? So in this case, we can calculate, as we said, talked about this. This is called the standard deviation. This is the square root of the mean square distance from the mean. So now let's calculate the standard deviation. So standard deviation is nothing but square root of variance. So we get that as $79,442. So this basically says, what this number says is that your mean is somewhere around 180,000, and most of your houses are basically within standard deviation is basically saying that roughly around 65-70% of your data should be between 180,000 minus 79,000, which is 80,000. So between 100,000 and 260,000, there should be somewhere around 65% of your data, right? So that's what it kind of says, that if you're within one standard deviation from your mean and one standard deviation below your mean and one standard deviation above your mean, roughly around 65% of the data stays, right? So that's something something that we infer from normal distribution. Don't get kind of, where did I get this number 65 from? You will learn that in the next chapter when we do inferential statistics. So now John's approach number 3. So John was basically set out to check that how far is the price of the house from the mean when compared to other points in the data set. So what he wants to do is basically 250,000 minus mean by random variation. Now we knew that standard deviation is a good measure of random variation. Range was one way, standard deviation is also one good way. So now we do that, and that's what we get. So it's 86.86, which basically means that it's within one standard deviation move from your mean, right? So that's fairly awesome. That is not very bad. So that's something that we have already seen here. So we can say that the price of John's dream house is 80.87 times away from the mean than the standard deviation, which is the root mean square of distances. So it's just one standard deviation, roughly one, right? 0.87 is roughly one. So it's within one standard deviation move from your mean, which is not an extreme value. That's all you can kind of say. When you do normal distribution, you would probably be able to appreciate how one standard deviation move is not a very big move, probably. And in fact, for outlier detection, this is what I was stating. A lot of times people use standard deviation moves above mean, standard deviation moves above median as ways to calculate outlier. For example, standard deviation, 3 standard deviation moves above your mean and 3 standard deviations below your mean are normally considered as outliers. So any value which is 3 standard deviations away from your mean is probably an outlier. So that's one definition of outlier. So just keep that in mind, that this is all that is saying. So yeah, so this is already okay. So this is something that I was probably gonna talk about in the next lecture. So 60% of, in case the data is normally distributed, you know, that perfect symmetrical curve, which is not the case here, right? Remember, our curve is not normal, it's slightly skewed to the right. But in case if it's a normal distribution, 68% of the data is within one standard deviation from the mean, and 95% of the data is basically within 2 standard deviation, and 99% of the data is basically 99.7% is within 3 standard deviation. Anything that is beyond 3 standard deviation probably an outlier, right? So that's the logic out here. In this case, our friend has his house within one standard deviation, right? It was 0.87. So that means his data is very well within the 68% of the houses, right? So he's not really buying a very expensive house. His house is within 68% of the majority of houses in New York City. So that's fantastic.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.